So the next one is also gonna be a little bit mathematical, but the math is not that hard. Okay, so I don't want you to panic when you see these formulas. How many of you know about Bayes rule? So that's it, only two or more. How many of you have heard of it before? Okay, so don't worry. This is Bayes rule. What I'm writing here is Bayes rule. So what happens with the Bayes rule? You have the probability, you want to compute the posterior probability of event A occurring condition on event B. So let's think about it this way. There is a jar in front of you and it's filled with coins. And these coins, they are gonna either end up being a head or a tail, okay? But the probability of it being a head is different among coins that you select from your jar. So what are we gonna do? We first select a coin, we first pick a coin from a jar that's gonna give us a coin. So the first step was B. Now the second step is flipping the coin and taking a look at the outcome. So that's what it means to condition. You first pick a coin from your jar at random. It's gonna give you the probability of your coin ending up as a head. So that's gonna give you a probability of the head. Once you know the probability of it being a head, you can flip the coin and then an outcome is going to come out. So that's event A. Event B is picking the coin from a jar. Event A is flipping the coin. Okay, so that's probability of A given B. And the rest of it is just multiplication. It's the probability of B given A, so you're switching. The role of the Bayes rule is that you're switching your events. A given B, and you want to relate it to B given A. A given B, B given A, and then you have probability of A being multiplied by probability of B given A. This is called the likelihood. This is the prior. For instance, your prior could be that most of the coins are gonna end up being a fair coin. Basically, 0.5 is the probability of either side happening, either being a head or a tail. That's your prior assumption. This is your likelihood, and then this is just the evidence, the probability of P. These are names, so just memorize them. It's posterior, likelihood, prior, evidence. But in the end, if you multiply P of A given B by P of B, that's the joint distribution of A and B, joint probability. So that is P of A comma B. So in the end, you have P of A, this is the joint distribution. P of A comma B is P of A conditioned on B times P of B. That's the definition. Similarly, you have P of A comma B is P of B given A, P of A. And in the end, the Bayes rule is saying P of A and B is equal to P of A and B. This is trivial, yes? So this part is trivial, P of A comma B being equal to P of A comma B. And then the rest of it is, one of them is this term, P of A condition on B times P of B. That's this term. The other term in the numerator is P of B condition on A times P of A. So the Bayes rule is just saying this. That's a very important identity. Okay, it says that if I know B, what is the value of A, sometimes solving this problem is difficult and solving the reverse is easier. So that's why you reformulate the problem in terms of P of B given A. So that's just a trick. Rather than working with P of A given B, you're going to work with P of B given A. And then this term, usually the evidence, is a constant that we don't care about. And P of A is an assumption that we make. Most of our coins are fair. That's an assumption that you can make. Maybe it's a bad assumption, maybe it's a good assumption, but that's an assumption that you make. Okay, so this part you know, this part is easy to compute, this part is constant, we don't care about, therefore you know P of A given B. This is powerful. I mean, Bayes rule is powerful. It has infinitely many applications. So it's better to learn about it in one of your courses. This could be the first time that you hear about it, but it's powerful. It's a powerful concept. Okay, now how are we going to use it? This is exactly one of those examples that computing P of ck given x1, x2, x3, x4 is complicated. We want to know the probability of the class being 1, 2, or 3. The probability of our flower being setosa, or versicolor. That's exactly what we are after when we do prediction. Given the sepal length, sepal width, if I know the sepal length, sepal width, petal length, petal width, what is its class? Or what is the probability of its class being a setosa? This is exactly what we want to find, okay? And it's complicated finding that. We just saw two methods of doing it, and we saw it was not easy. This is complicated, but then we are going to use the Bayes rule. We are going to switch the role of x and c. That's the first part. It's going to be p of x1, x2, x3, x4, given the class. If I know the class, it is easier to know its coordinates, the sepal length, sepal width, etc. Okay? If you know the class, it's easier to understand that. P of ck, you just count. We know that out of 150 observations, 50 observations were setosa, 50 observations were versicolor, and 50 observations were the other class. So one third, one third, one third is going to be the values that you put here. So that part is easy. This is a constant we don't care about because it doesn't depend on our class. It doesn't depend on C. So that part we don't care about. So far, it's just Bayes rule. Everything is perfect. So we are not making any mistakes. It's perfect. But then here is when the naive assumption comes in. And the naive assumption is that actually, before we do that, let's look at the numerator. It's P of x1, x2, x3, x4 given ck times P of ck. That's the numerator, as this term. And we know that that's just a joint distribution. That's what I did up there, is the joint distribution. In this case, A is x1, x2, x3, x4, and B is ck. So that's the joint distribution. We can break it apart by conditioning, by changing what is your A, what is your B. Now let's say your A is x1, your B is x2, x3, x4, ck. So you can break it that way. Then you can take a look at this term, copy it here and break it. x2 given the rest. Then the same thing here. And this is where the naive assumption is going to come in. P of xk, x1 given x2, x3, x4, ck. You can just say it doesn't depend on x2, x3, x4. You're just saying that if I know the class, I don't need to know the other coordinates. So this is the naive assumption. That's an assumption. We do the same thing for x2. This is where the naive assumption is going to come in. And this is yet another naive assumption. If I know ck, I don't need to know x4 for me to be able to make a prediction about x3. I'm going to stop here and try to answer a couple of questions, and then we are going to take over on Monday, the rest of it. But in the meantime, you can learn about Bayes rule a little bit, read about it. It's really powerful. It's good for yourself, good for the future. Any questions?